Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body, in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of